So welcome to the first lecture in this session on random numbers and random number generators for ECE 3340 numerical methods. So there are three things that I'd like to talk about for this, and that is, so first I want to give an overview of probability, and then discuss two major distributions, the Gaussian and uniform distributions, and finally conclude with some details about the central limit theorem and how that's helpful for us. So what a probability does is describes the likelihood of some random variable taking on a value. So the probability that a variable x will take on a value in an interval between a and b is given by the integral of this probability distribution function p from a to b. Now this p function is the probability distribution function, or PDF. Now, an alternative formulation uses the cumulative distribution function, which is a pre-integrated version of p. And what the CDF provides is the likelihood of a value of x taking on a value less than the parameter. So for example, if we want to determine the likelihood of x taking on a value less than b, we can plug b into this c function, which provides us with a pre-integrated form of p from -infinity to b. So if we want to evaluate the probability of x taking on a value between an interval a and b, which is the most common use for a PDF or a cumulative distribution function, then we would plug both a and b into the cumulative distribution function c and calculate the difference. This would give us the probability that an unknown random value x will, once it's measured, take a value between a and b. So let me give a couple of different examples for a few different distributions. So here is a uniform distribution for or three different uniform distributions and their corresponding cumulative distributions. So the first is a distribution specifying that an unknown value x can take on, or an unknown random variable x can take on values between -1 and 1. And what the cumulative distribution is telling us is that if we ask what the probability is that x will take on a value less than -1, if we plug in -1 into this CDF, then we'll get 0. So there is no possibility of x taking on a value less than -1. Now if we plug 1 into this CDF, we'll get a value of 1.0, indicating that x has a 100% chance of being less than 1, or less than or equal to 1. Now, if we squeeze that distribution a bit, we take the half the range of it from 0 to 1. So now x can only take on values in the range of 0 and 1. This effectively doubles the probability for any given value, and that increases the slope of the corresponding cumulative distribution function. If we make that range even smaller, then the probability for any given value increases proportionately, and that's because the integral of the probability distribution function, the PDF, has to always be 1. So as the cumulative distribution function moves to the right, as it moves out to infinity, the cumulative distribution function has an expected convergence to 1. All right, so now let's take a look at a more common distribution, the Gaussian distribution. And here's the corresponding cumulative distribution function for the Gaussian, which is a sigmoid. Now, if we want to determine what the probability is of a random variable x taking on a value less than -1, then we would just look up the value of -1 in the cumulative distribution function, And this would tell us that the probability of x taking on some value less than 1 is equal to c at 1. We can do the same thing if we want to know the probability of x taking on a value less than 0. We just look up 0 in the cumulative distribution C in order to read out the corresponding probability. Now, the more common case is that we're interested in the probability of x taking on a value within some specified range, in this case between -2 and 2. So in order to evaluate that, we look up -2 and 2 in the cumulative distribution function and calculate the difference between those two to determine the chance that x will lie within this this region. All right, so let's look at the analytical representations of these two distribution functions. So a uniform distribution, as I mentioned, a probability distribution function always has to sum to 1. The integral has to always be 1. So if we're given a range a and b, and and where this is the range of values that the random variable can take. Anything outside of that range is going to be 0. There is 0 probability that the random number will take on that value. And anything inside that range, if the probability distribution is uniform, will take on a value of 1 divided by b minus a, which is just the size of this interval. Now, the normal distribution is a Gaussian given by this exponential function, and there are two parameters for this Gaussian, the mean mu and the standard deviation sigma, that define the variance. Now, the reason that the Gaussian distribution is so common is because of the central limit theorem, which specifies that the sum of a set of independent variables converges to a Gaussian distribution. So if we have a set of random independent variables, x1 through xn, that have different PDFs that are not necessarily Gaussian, they will converge to a Gaussian distribution. Their sum will converge to a Gaussian distribution. Now, I can give an example of that in a fairly straightforward case. So take the case of a six-sided die. A six-sided die, a perfect six-sided die, has an equal probability of landing on any of the 6 sides, 1 through 6. Now, if we look at the probability distribution, so this is an example of a uniform distribution. If we look at the probability distribution of the sum of 2 six-sided die, then we get this pyramid shape where the probability of the sum being 7 is significantly higher than the probability of the sum being 2 or 12. And that's because there are more values of the 2 die that will sum to 7. So for example, you can roll a 6 and a 1, or a 5 and a 2, or a 4 and a 3. But the 2 requires that both dice roll a 1. The 12 requires that both dice roll a 6. Now, as we increase the number of dice and look at their sum, we'll see that they converge to a Gaussian shape. Right. So here is a very basic demonstration of how the central limit theorem works. Now, here's an example of a more practical demonstration, and that's human height. So human height is based on a large number of complex variables, resulting in an output that is Gaussian distributed. So if we take one of these parameters, in this case sex, and we plot the Gaussian distributions for both men and women, the height of men and women in inches, and their corresponding cumulative distributions, we can see that there's some difference between these distributions, but it also allows us to query this data in some way. So for example, we'll take the case of my wife and I, who are both 5'7", or 67 inches. So if I look up the probability of me encountering someone that is shorter than I am, right? All I'd have to do is look up 67 inches in this cumulative distribution function, and I'd have a chance of 22.6% of encountering someone shorter than me. That's because I'm shorter than the mean. I'm shorter than average. My wife, on the other hand, has a 71.6% chance of encountering a shorter woman because she is taller than average.